Good morning, Professor. Thank you for giving me this opportunity to express myself. My name is Amod Kumar. I am currently a internship student in National Yang Ming Chao Teng University, Taiwan, under the supervision of Dr. Neil Tumiti. The professor is also working on the 2D materials, and I am very interested to join your lab. So, uh, I just I just complete my MSc in 2023, and I just complete my BSc 12 and 10 from the India, and these are my percentage. So this is the subject which I learn in the MSc. These are in the two semester which I just focusing on the core subject of the physics, and after the semester third and fourth, we are the focusing on the mainly on the material science and uh, prepare a report and present my presentation and defend a thesis in the front of the many professor, and one professor come from the outside. Oh, sorry. During the MSc, I just mm, know about the some instrument, how to synthesize the material with the help of the solid gel technique, solid state, hydrothermal. So hydrothermal is mainly used for the when I want to prepare rod-like structure. So I am using very much solid gel method. I think I use solid state also, but I think solid state is good for the preparing the sample. And cyclic voltammetry. Cyclic voltammetry, uh, this instrument is used when I am working on the supercapacitor also. Uh, uh, After the preparing the material with the help of the solid gel method and make device, after that, with the help of the cyclic voltammetry, we calculate the capacity of the your device, power, charging, discharging, and many things. And these are all this buccal furnace, ball milling, tubular furnace. Just these are the known. Computational skill. So I have the work on the quantum espresso, the simulate the Bismuth ferrite, and I work on the Sista for the simulation. Even I Sista I learned in the workshop which is held in the JNU, New Delhi, India. Full prop is and full prop is a very interesting thing for the material science student. With the help of the full prop, we calculate mm, the crystalline size, and the phase will be changed or not. Yeah, with the help of the origin, we plot the many all the data and C programming and no programming, and because it is in my course in my thesis is on the dielectric relaxation behavior and conjunction mechanism of UN and MN post-substitute multiple different fractures. So my work is on the side of dielectric, and my main sample is bismuth ferrite. I dope mm, Mn or U in the bismuth ferrite under the supervision of Dr. Pawan Kumar, which is the assistant professor in Mahatma Gandhi Central University. So I want to describe not more, but in quick form about my thesis. So multiple materials. So, multiple are those materials which exhibit more than more than two ferric properties, just like if here is the ferroelectric, ferromagnetism, and ferroelastic. So one is magnetoelectric effect. Magnetoelectric effect is the those ferroelectric material which exhibits ferroelectric and ferromagnetic. That material will be called ferro, sorry, magnetoelectric effect. So from the figure, I want to describe some point in the quick form. So there is the ferroelectric. So after the applying the electric field, charge will be the polarized, and there, and after the applying the magnetic field, spin is aligned. So these two properties present in the one material, the ferroic material, is called multiferroic material. So application of this ferroelectric in the memory devices, sensor, microelectronic data storage, and spintronics. These are the things. So there I want to describe some point also. There are some points on the bismuth fluoride. So why I am interested in the bismuth fluoride? So it is an inorganic chemical compound perovskite structure. It belongs to the rhombohedral crystal symmetry with the uh, space group is R3C. And not only this, it's a good, and we are interested in U and Mn. O substitute U and U doped at the B side and Mn is doped at the Fe side. So why this? So after the doping of the U, it's increased the dielectric constant and dielectric behavior of the bismuth ferrite. And Mn, when I substitute at the Fe side, then it's decreased the oxygen vacancy. So these two enhance the property of dielectric constant. So actually, I want to say this, so I dope this. So I dope it in the 1.5%, and let's describe further. So this is the pictorial representation. Through the help of the pictures and the some chemical, I describe how I prepare my sample by the Solgel technique. So mm, first, I take all the sample in the beaker and sonicate it with the nitric acid or just DI water. DI water only is in, no, is not visible. Oh, no, maybe it is. Nitric acid is DI water, and all these four samples with an nitric acid and sonicate it individually and put in the one vessels. After that, we put it on the hot plate and put the magnetic bit in it for the mixing or moving, and take some temperature and increase the RPM. After the 3 to 4 hours, it's come in the gel form, and this, and when it is come to gel form, we have to pick out the magnetic bit in it and increase the temperature. Then it's come in this form. There is a mobile furnace. Due to the video, maybe it's not visible. So there, I put in the mobile furnace for the whole night. At the take the temperature is 100 degrees, and day after that, I put out this, and the sample it look like that. Then we grind it, and after this we send for the XRD to confirm it which I want to prepare this sample. It's uh, mm, it on that it is or not. If it is, so we have to increase our doping just 0% and anything, whatever you want. So I go further. So after the several attempts, I prepare the BFO and substitute some percentages, some substitution of U and Mn in the 2.5%, 5%, and 7.5%. So these are the XRD of the doping. So this figure is the uh, intense peak. This peak, zoom part of the intense peak. So in the lower doping, so there is the no doping. It's a pure BFO. Then it have the two peak, but after the increasing the doping, the two peak will convert in the one peak and sit at the right side, higher degree. It is due to the stress and strain and due to the phase change. So how I know it's due to the phase change. So at the previous, I told you about the ritual refinement. I do the ritual refinement of the each exciting, and it's confirmed that the phase will be a change. The phase will be the phase of the BFO is R3. And sorry, the space group of the BFO is R3C. But after the doping, it's converted into PBNM. And phase is the rhombohedral. It's changed into hexagonal and many other things, but to the mesentery. So these are the factors due to the this. Its two peak will converge into single peak and it's shift in the higher degree. And with the help of the exciting, uh, we calculate also crystalline size. So only this, where is the cursor? Oh, with the help of the cursor, I show that this is the Williamson Hall plot. With the help of the Williamson Hall plot, I calculate about the crystalline size, strain, delocalization, and one thing is, or through the help of the Sherrod formula also, we can calculate about the crystalline size and strain. And with the ritual, after the ritual refinement, we can also confirm, it's confirmed the phase change also, uh, and uh, crystalline size, and many things we will calculate about the material through the ritual refinement. So go further. So this is mainly about the dielectric characterization. So I'm mainly focused on the dielectric in my thesis. So from the first figure, from first figure is between the dielectric constant and the frequency. As you see there, after the increasing the sorry, sorry, after the increasing the temperature, dielectric constant will be increased, and after the increasing the frequency, dielectric constant will be decreased. It's due to the oxygen vacancy, and this figure at the lower frequency is due to the don't know where is of cursor is going from there. So this figure is so like that due to the polarization. So there is the four types of polarization as you know, dipolar, ionic, electronic, and many uh, interfacial. Also. So due to the this polarization, the graph will be look like this. And do not go in the deeper. So only describe the few things about the figure. So this is the fitted graph. This is fitted to the modified divide equation. Only I fit their figure is shown only the 250 degrees Celsius. So uh, through the help of the this fitting, I know about the spreading factor, relaxation time of the materials. So individually, I will put the all the at all the degree, that's 50, 100, and many other. But there I saw only there 150 degree Celsius. So there is the dielectric loss factor. So as the previous one, this is also after the increasing the temperature, dielectric loss will be increased, and with the frequency, dielectric loss will be decreased with the frequency. So one thing is important there, the development of defect induced dipole due to the localized electric charge carrier hopping are the main cause of dielectric loss. So, and this is the figure 4. This is the Johnson power law. Through the help of the Johnson power law, I describe about the which types of model is fit uh, with the help of the Johnson power law. So there is so 1 minute, there is the cursor. So this formula, so is this formula is sigma AC and sigma DC plus A omega S. Power is the very important. So in this fitting, just we fit this and after that we get the S and we draw the graph between the S between the S and temperature, and we know which types of model is it is. If S is increased with the temperature or S will be decreased with the temperature. If S is decreased with the temperature, then it is correlated barrier hopping. And if it is increased with the temperature, this is a small polaron conduction. So in the my case, it's correlated barrier hopping because it's decreased with the temperature. And the figure 5. Figure 5 is the graph between the Z double dash and Z dash. So in this, the complex impedance plot, this figure is also called to and so with the help of the cursor. Huh. This figure is mm, is fitted due to the Cole plot. And with the help of this figure, we describe about the grain boundary, uh, uh, grain surface, and we want a semicircular plot. If it is semicircular, then it is good. So at a higher temperature, it look like a semicircular. Just so it is at a 100, 250 degrees Celsius. It look good in semicircular. So and uh, we describe through the help of the grain resistance, grain boundary resistance, uh, grain capacitance, grain boundary capacitance, many things we describe about this. So and one of the figure is there is Z between the Z double dash and the frequency. So we'll look, there is the peak, there is the many peak, one is there, and many peak. So what peak want to show and express with the help of the this graph. So uh, the peak is the on the left side at the lower frequency also, it is the higher frequency also. The lower frequency say another thing, higher frequency say another thing. So, uh, peak will be described the presence of the electrical relaxation in the co-doping compound. So, the observed peak is oriented due to the defect charge carrier. And if this peak, so where is the, if this peak at the lower frequency, then it is due to the grain boundary. And when this peak at the higher frequency, then it is due to the grain. So, and many other figure I also describe in my thesis, but we have the low time to describe all the things. So, go next. So, I am just so all things. Uh, I done a one internship in Indian Institute Technology, which is IIT in Patna, under the supervision of Dr. Monranjan Kar. And my summer internship topic is fabrication of supercapacitor for the energy storage device application. So, as you previous describing about the sol gel method, I attempt very much, and after that, I'm going to have done this preparation with the help of the sol gel method. And there is the some sample also. So we put many sample to enhance the property of the materials. So this is the double perovskite materials. With the help of this, we want to see the mm, cyclic biochemistry. So, so put these materials and prepare a device through the help of the spin coating, and it's a symmetry. So at one side is the uh, spin coating copper sheet and material in. I show in the this figure there. Uh, After the spin coating look like that, and two is the similar, and between them I put the separator, and we check the uh, CV, the oxidation and rejection of the ion, and it go from this symmetric plate to this symmetric plate, and with the help of this, we calculate about the capacity of my device, capacity, power of the device, and describe about the charging discharging time. So it's from there, its device is not more good, but we are trying to do the best. And this graph is between the Z dash and Z double dash, which is describe about this material. So this is which I done in the summary internship. So next, so currently, currently I am in the uh, Taiwan and just working under the supervision of Neil Tumiti. The institute name is National Yang Ming Chong University. This is the 3 month internship. So I am here for the 1st November to the 31 January 2024. So mainly I am, so their topic is the working on the topic is the thin film growth of the semiconductor and insulating material using the CVD and PVD method. Material is HBM graphene. So here I learn about all these things. So firstly, I am there to learn more paper about the 2D material because HBM are the 2D material. So there, uh, when I came there, first assignment is to prepare, learn about the more about the 2D materials and learn about the Hall effect experiment. So I am trained by the one trainer and I take a small test in the front of the professor. Then I am eligible to do this experiment with myself. So I pass it, and then through the Hall effect experiment, I know about the uh, which types of which it's a N type or P type mobility, seat resistance, seat resistivity, and many things we know about the. If you, I am working on the semiconductor, it's a Hall effect experiment is the good. So I, through the help of this, I describe about the Van der Waal port because there is the Ford Pro. I just put the sample in it, and this is the 1, 2, 3, and 4. And after that, here we check about the each N type of P type and many other things. So after this, I am learned about the chemical vapor deposition. So here, this is the furnace, and this instrument. With the help of this instrument, I control the plasma uh, and gas, gas like hydrogen, argon, many things. And we put the substrate is there, and the which I want to deposit just HBN, HBN is the there. So I am here to just uh, grow HBN on the copper sheet, and after the growth, I transfer it into the paper and take the Raman to confirm it, and take Raman IV and XID to many things to it's or not. So I do this in the 3 to 5 times, and I am comfortable to do this experiment. So I am currently working on the physical vapor deposition. So So there. So next, due to the lost time, oh, this is the my achievement, and this is the workshop and conference which I attend, and one of the paper which I submit to the journal, a journal of electroceramic, and it is under review in the 1 to 2 month, 2 month maybe. So thank you, thank you for the listening me, and thank you for the giving the opportunity to express myself. I am waiting for your good response. Thank you.